So thank you very much again for taking this trouble to give this late evening lecture.
No problem.
Okay, I have made you already a co-host, so you should be able to share your screen. So let's give a shot.
Okay, so yeah, I'll share the screen. Can you see the screen?
Yeah, something is coming. Yeah, okay, I can see your screen now. Cool. Do you have any animations or any videos in your lecture?
Yeah, actually quite a few.
Okay, so maybe we can just give a shot on one of those slides. It should work, but just in case.
Okay, yeah, so you think that there would be a kind of delay?
I just started the recording button. So, good morning, everyone from Indian subcontinent, and maybe good evening or early good morning to people in Europe and United States. So, it's my great privilege to welcome all of you to this lecture by Professor Bransilav K Nikolic. So he is from University of Delaware, where he's working as a professor in physics. You may know he has really done outstanding work in the field of spintronics and magnonics. But I just very briefly mention about his biosketch. He is also working as a senior visiting scientist at RIKEN in Japan, which is very famous for spintronics. He received his PhD in theoretical condensed matter physics from Stony Brook University and the BSc degree from the University of Belgrade, Serbia. He was a visiting professor at the University of Regensburg in Germany, National Taiwan University in Taiwan, Center de Physique Théorique, the Grenoble Alps, and Beijing Normal University. His research is focused on non-equilibrium anybody quantum systems, first principles quantum transport, multi-scale quantum classical approaches, and high-performance computing applied to nanostructures of interest to spintronics, nanoelectronics, thermoelectronics, chemical physics, and nanobiointerface. So he's really working on a really large area of topics. So again, I thank him for taking the trouble to give the lecture almost midnight for him. And I just like to request all the participants, if you have a question, you can write that in the chat window or raise your hand. And at the end of the lecture, we will take definitely all the questions one by one. So with this short note, so I invite Nicholas to start his lecture. Thank you.
Okay, so thanks. Hello, everyone, and thanks for this kind invitation. As you know, we are all locked down for now almost a year, and there are good things such as this, ability to give talks at arbitrary long distances, and we just tested the equipment, and I hope that you will see everything working, including a lot of movies, without any delays. But of course, hopefully one day we can all meet and have a discussion in person, because, when you're talking into your screen, it's becoming a little bit daunting, you don't know what's going on behind, and you don't get this kind of response from the audience, and usually the discussions with these Zoom talks are not that easy. So the most important thing, aside from the title, which you have already received through the abstract, is actually this website address. So any reference on my slide that you see in red link, like PhysRevB or nanoletters or anything like that, can be quickly downloaded by going to this website and clicking on this publication. So this saves you time and money, because you don't have to go to the publisher website, search for my papers, then get, this licensing and stuff like that. What I have found myself when I watch the Zoom talks, things fly fast. Usually there is a big audience, you cannot ask questions, and then I just record, what are the references that the speaker is advertising, so that I can avoid, wasting time on searching myself. And then after the talk, I usually spend time downloading PDFs. In this case, the PDFs can be obtained really easily from our group website. If you participate or are interested in any way in world politics, you probably know that there is a new president in town in the United States, Joe Biden, who actually lives something like 15 kilometers away from our campus. This is marked on this map, and our campus is halfway between New York City and Washington, D.C. And there is some also history why the Delaware is such a small state and still independent, which has to do with Swedish colony from this time and so on. So the host has mentioned that I work on many things, but I'm really like a sort of representative of a team of people working together rather than I myself work alone on all these topics. And it is actually a great pleasure to give this talk for audience in India, because currently, in the past, let's say, 5 years, all of my best students actually have come from India, and they are really pushing much of the stuff that I'm going to talk today. And also, there is an important postdoc who worked on this, who recently moved to a new position, and there was another postdoc working on this a few years ago. And I also collaborate with Professor Plehach from our mathematics department, because eventually all of these physics equations have to be solved in as efficient as possible machinery of numerical linear algebra. So here's some kind of fun article, and I have added on the top of it also, like, even the talks could be obsolete. So you can Google this. It says, the scientific paper is obsolete. And I'm mentioning this, it is not really that, our research articles are obsolete, because this will be the major medium to communicate, taking into account that the knowledge in the books is always kind of behind the research literature. But they really think about paper, physical paper. And we know this because these days you don't really read anymore anything printed on paper. You really download PDF, as I offered you 3 minutes ago through that link. But what they really say is that it's not just that even PDF would be obsolete, because the things should be now interactive. So in some of my other talks, which are kind of more boring and mathematical, I do give every participant mathematical notebook so they can actually do something during the talk, move their fingers, move their body, and so on. In the case of this talk, it would take too much time for you to run, let's say, some Python notebooks that me and Dr. Petrovic have set up, including spintronics, for some of the courses we give at University of Delaware, which are, by the way, publicly available from another website. But what they really advocate is, put Python notebooks and animations and interactive stuff into your research papers. And in the case of this talk, that kind of interactivity will be movies. So this is a good news, because even if you miss, let's say, some difficult equations, and I'm not going to give more than one slide with equations, or, you miss some concept just because I'm talking and, time is flying, you should still be able to capture the essence of this stuff I'm going to discuss today by watching this movie. So what I'm really saying is, even if you're taking breakfast now and maybe missing some specific slide, when you see the movie and something running and we test it and everything is working fine, even over this distance of many thousands of kilometers, you should really pay attention to these movies. So here is actually animation that you should see now. So original spintronics, they started, let's say, with spin valves and magnetic tunnel junctions, for which Nobel Prize 2007 in physics was awarded, was all about having magnetic layers whose magnetizations are either parallel or anti-parallel, and any kind of moving electronic spin is also parallel or anti-parallel to these localized magnetic moments. And this is what people usually call colloquially first-generation spintronics. But the modern research in spintronics, and you're going to hear about it from excellent speakers, as I just learned, such as Pietro Gambardella and Hyun-So Yang, in the next few weeks, is largely focused on this next generation, where you have, for example, localized spins inside the magnetic material being tilted with respect to each other, which is called non-collinearity. Or you could have electronic spin, which is hitting one of these localized spins, and that electronic spin is also not parallel. And once you have these dynamical, so-called non-collinear magnetic textures, you can do many things that were not possible to be done with this original spintronics. So in particular, for example, IBM has given up on much of the hard drives and any kind of basic research in graphene and carbon nanotubes, but they still have a large division devoted to this so-called racetrack memories. And there was an animation running here. Racetrack memory would be an array of magnetic domain walls. For example, this red would be one domain, all spins pointing up. Blue would be another domain, let's say all spins pointing down, and then in between would be a transition region. I'm going to illustrate in a moment. And these domains could then store ones and zeros of information. And if you succeed in moving these domain walls by, let's say, current or magnetic field, then you would read that information by some read head's position here. And you could actually store a lot of information. And if you can move this information with very little current, then you would also substantially reduce dissipation, which is always the name of the game in much of the spintronics. And that would be like a perfect example of a non-volatile, low, ultra-low power consumption memories for digital electronics. And you could even create a logic, and you could have logic in memory and all kinds of nice things. So Stuart Parkin, who patented this, he has been talking about already version 4.0 because they are changing the type of materials they use for this. Of course, nobody has ever made this to the point that it would become available for any kind of device applications. And there is also a new kid on the block, which is you can do this with skyrmions, which are even better than magnetic domain walls because you can move skyrmions by injecting current, and they would not be perturbed by any impurities, unlike magnetic domain walls, because they have extra topological protection in real space. And then once you have these magnetic domain walls, you can also have even other types of computing applications, such as so-called neuromorphic computing. You could be creating basic neurons, neural cells for neuromorphic computing, and there is even a proposal to create a qubit for quantum computing using this macroscopic magnetic domain wall. So let's actually immediately illustrate, even though this is something that you have in everyday life, because your fridge magnet is actually just a bunch of magnetic domains and domain walls. So this is illustration of magnetic domain wall. So this will be magnetic domain wall inside the magnetic nanowire, obtained very early on when the first micromagnetics codes, and some of you might be using these codes, became available. So there is one domain when the all localized magnetic moments of the ferromagnet point to the right. There is another domain when they all point to the left. So this is called head-to-head magnetic domain wall. And then in between, to minimize the free energy, there has to be a transition region when they are changing from point to the left to point to the right. And if the wire is less than 50 nanometers wide, then you have this head-to-head domain wall formed as energetically favorable. If the wire gets thicker, then you can also get this vortex type of domain wall. And if you try to integrate these angles of these sticks, which are basically classical description of these localized magnetic moments, you might even get some topological charge in specific directions. So one important thing for my simulations and later calculations in this talk, since it would be very expensive to simulate these 50 nanometers wide wires, is that most of the examples would actually be just a slice in one dimension to get the basic physics and engineering out of this. So we're just going to consider a bunch of spins lined up in non-collinear fashion to generate this head-to-head magnetic domain wall as the prime example that you can play with, which is also realized in this less than 50 nanometer wide magnetic nanowires. So this was the previous slide was magnetic domain wall in equilibrium, but as I mentioned, the real name of the game is to push them by current, and then they start moving, and that becomes domain wall out of equilibrium. And most of the stuff I do in my research with my group is non-equilibrium quantum many-body physics. In this case, it's non-equilibrium quantum classical many-body physics, because we're going to consider electrons quantum mechanically and this locally spins classically. And so once you inject a current into the domain wall, that current of electrons could be reflected or it could be transmitted. And either of these processes is going to exert a force or a spin torque, and all of these effects should be somehow described and taken into account so that you figure out eventually how the domain wall is going to move under the flux of injected electrons. And here is immediately important slide, one of these important slides because it contains a movie. So imagine I take a simplest example of this magnetic nanowire in strictly one dimension, and I inject from the left a flux of completely unpolarized electrons. And so now what you see is that these white sticks are fixed. They are going to polarize my electron in the direction of the white stick. And as long as electron is flowing through this region of parallel white arrows, nothing happens. But once electron comes to this region when its spin in the direction of the white sticks is not parallel to this, and let me run the movie again to see this clearly. So once electron comes into the region of this domain wall itself, which is this region here, which is now moving, then the electronic spin is not collinear to one of these fixed y spins, and that will ensue in the so-called spin transfer torque. And once the torque is transferred onto these local spins, then they start precessing, and that precession eventually looks like as if some perturbation is propagated from the left to the right. So this is the first effect to pay attention, which is that once you inject electrons onto the domain wall, they're going to exert spin transfer torque onto the wall itself, and the wall is going to start propagating from one position to another one as long as that current pulse is active. And because of that, to be able to follow the rest of the talk, we need to go through this crash course on the so-called spin transfer torque, which is again one of the most important topics in contemporary research on spintronics. And perhaps depending on your background, after this slide, you're going to get enough knowledge to both follow my talk as well as follow the talks of Hyun-Soo Yang and Pietro Gambardella, who are most likely going to talk about this phenomenon in additional presence of spin orbit coupling. So this is what spin transfer torque is. You have to have, at least in the original prediction, they're going to talk about spin transfer torque with one layer. You have to have two ferromagnetic layers. You inject unpolarized spin unpolarized electrons. They get polarized in the direction of the white magnetization. And the important thing is that white and black localized magnetic moments, which summed up give these two magnetizations, are not collinear, not parallel to each other. And so the electronic spins, which are these red arrows, are now polarized in the direction of white magnetization of the fixed ferromagnetic layer. And once they impinge onto the so-called free layer, quantum mechanics says that the only component which can go through is the component that is parallel to the black magnetization. And that means that any component which is transfers to the black magnetization has to be absorbed. And then the question is, what happens to that absorbed component? And that absorbed component is going to be deposited into the free layer, and the free layer is going to get a kick. And how is that kick then calculated? Well, if you assume that the black magnetization by magic, and I'm going to explain in a moment what is included in that magic, can be treated as a purely classical vector, then you're going to get some classical equation, which we call Under-Lifshitz-Gilbert equation, and that classical magnetization of the free layer is going to feel the torque due to external field. It is going to feel damping due to spin orbit coupling and phonons and some other processes I'm going to discuss. And then this deposited torque is going to be decomposed into two additional vectors. So at the end of the day, you have a problem with four vectors. There is a differential equation of first order, And of course, you cannot know what the solutions are. They could be even chaotic because the equation itself is nonlinear unless you solve this equation with given initial condition. The important point is that there are many formalisms of how to calculate the torque since the original prediction of Slonzewski and Berger in 1990s, but today the most efficient way to think about torque on localized magnetic moments described by classical vectors, independently of whether the spin-orbit coupling is present or absent, is to basically think that you have to have or calculate this or measure this non-equilibrium spin density, which is a quantity arising due to the electronic spin and the flow of current, and then you take a cross product of that quantum mechanical expectation value, which at the end of the day is going to be triplet of three real numbers, with the direction of this unit vector along the free magnetization, and that is going to give you torque. So if I split this TCD into two components, DL and FL, which compete with the damping or this a magnetic field, then we talk about damping-like and field-like torque, or in this case, we talk about equivalently a torque in the plane of two magnetizations, which is the damping-like, and torque out of the plane of two magnetization, which is the field-like torque. And once you have this torque, what it means is that you're going to manipulate orientation of the black free magnetization by injecting current, or in practice, you're going to inject current pulses. And that opens up an array of 7 different applications. So for example, if you succeed in switching this black magnetization from up after it performs some motion to down, you have changed the state of magnetization from, let's say, digital 1 to digital 0, and that becomes the source of binary memory, which is actually already part of commercial world. So there is a small company, and you could invest even your money into it and hope for the best and maybe become a millionaire in a few years from now. So the company is called Everspin. So this is like a free, advice, not that I'm giving it, but if you believe in spintronics, put your retirement into Everspin, and they make these devices that are superb non-volatile memories, much better than, let's say, the standard flash memories you use in your digital cameras or cell phones and so on, but they still do not have very high capacity, and they're not really sold to regular customers. They're sold for special applications, satellites, data centers, and so on. If this magnetization starts flipping chaotically between up and down, that becomes a perfect random number generator. Then you could have a motion depending on the relationship between these 4 vectors in which this magnetization is just steadily precessing. In that case, you would obtain a microwave oscillator of picowatt strength and nanoscale size. You could have a microwave detector, and you could have a MEM resistor, which is element of neuromorphic computing, as well as a system which emits spin waves or magnons. So you can have all these 7 beautiful applications once you have a functional tri-layer of these non-collinear 2 magnets, and you're injecting current pulses. And again, once you listen to the talk of Gambardella and Hyun-Soo Yang, you're going to see exactly this story with exactly this equation, but in that case, there would be only one ferromagnetic layer, and this guy would be generated with assistance of spin-orbit coupling, which I also have in some of our research and in a different talk. It's not going to be a major topic of today's talk. So one thing, if you're like, let's say, theoretical physicist or theoretical engineer working on spintronics, you might ask yourself, what justifies the treatment of this free magnetization as a classical vector? And the answer is nothing. In principle, spin is a purely quantum mechanical degree of freedom. You can see that easily, like even from undergraduate or elementary, high school, whatever, in India and Europe, quantum mechanics, which is that spin space is always added separately on the orbital space. The orbital space does have a counterpart in classical mechanics, but this guy doesn't. Spin does not exist in classical mechanics. There is some subtlety about representation of Galilean grooves, but spin is always considered to be internal degree of freedom, and you would always have to treat spin by assigning a quantum mechanical operator. And this is, for example, what we do in some other branches of our research and other talks that I'm going only to mention here. And in this branch of research, which we call quantum spin torque, which has started over the past 2 years, we actually treat both electronic spin and localized spins, which are red arrows in this case, quantum mechanically, which means we assign quantum mechanical spin operator to electronic spin, and we assign quantum mechanical operator to these localized spins, and that of course is much more complicated business than what I have started to talk by considering this localized magnetic moments as classical rotating sticks with arrows. For various purposes of formalism of non-equilibrium many-body theory, which is our major bread and butter in daily life and practical work, you would like to map these quantum mechanical spin operators to bosonic operators, because green functions basically do not like original local spin operators, they like bosonic operators, and this is another approach that we have been working on, and in a few days I will be putting this paper online that is going to explain some new tricks on doing this beyond what you typically find in textbook literature on magnetism using the so-called Holston-Primakov transformation. But today, in today's talk, and that's the essence of the talk, I'm actually going to discuss this formalism, which is much easier to handle, and it can handle many more localized spins and larger physical systems, which consider electrons quantum mechanically, and it considers localized spins classically. And this is what I call 3 roads to non-equilibrium electron-magnon interacting systems. Like in some other fields of physics, they talk about 3 roads of quantum gravity. And in their case, it sounds much deeper, but of course they cannot test the 3 roads. In our case, each of these formalisms could be tested against experiment. And once you do that, you can actually see which formalism is applicable at which limit. So this formalism is typically what people could be using, including my next slide on classical micromagnetics, when you perform standard experiments in spintronics with orientation to room temperature devices for widespread commercial usage. So like any kind of room temperature spintronics typically appears to be describable, and Gambardella describes his experiments, as I'm going to show in a moment, using this kind of approach with classical rotating sticks if your experiments are 300 Kelvin. But if you go to very low temperature, and this whole field started by Sergei Rajdin performing experiments at around 3 Kelvin on exactly the spin valve from my previous slide, then you would start seeing things that cannot be described by considering localized spins as some kind of sticks rotating in space as classical vectors. Instead, you would have to switch to this formalism when everything is considered quantum mechanically, and then the whole problem becomes a very complex quantum non-equilibrium many-body problem. Just to mention, like when we did this paper in 2014, we were able to handle, let's say, 3 times 3 localized spins fully quantum mechanical. In these papers, we typically do maybe 10, 20 spins, and that's the limit with even the presently available supercomputers, GPUs, and stuff like that. If you use this quantum classical formalisms, you could handle thousands, 100,000. If you do purely classical spins, millions of these classical spins. So the computational convenience is also something which determines like which of these formulas you're going to use. So if you're an experimentalist, or let's say electrical engineer, you might find yourself doing just purely classical modeling, which means there are no electrons in your calculations. Instead, you download one of these codes, and now you can find a lot of online tutorials, both for OOMF and MUMAX, that are running whole summer through this online spintronics seminars. Go and check their websites if you're interested in this. And I have seen, for example, before COVID, one experimental colleague showed me his laboratory, and half of the lab was all GPUs running MUMAX day and night, and another half was real experiment. And he was telling me that he's checking what to do next in the lab or interrupting experiments. So many experimentalists do their own theory. They don't need any help from any theorist if they do these micromagnetic calculations. And what these codes are doing, they're solving this Landau-Lifshitz-Gilbert equation. So if you're solving Landau-Lifshitz-Gilbert equation for just that black single spin, the so-called macro spin from my ferromagnetic trilayer, then you would only consider these yellow terms, which means you have a dm over dt, that would be that free magnetization is equal to minus gamma m cross h, which is that effective magnetic field causing precession. This would be the so-called Gilbert damping introduced phenomenologically. This constant could be actually calculated from some complex DFT first principles calculations. If you, on the other hand, consider magnetic domain wall, which means you have to consider dynamics of these individual sticks one by one, then you would also add these two extra terms called adiabatic and non-adiabatic torque, and they turn out to be very important. When you perform these purely classical micromagnetic simulations, you can see that magnetic domain wall is not going to move at all unless the current reaches some threshold, and that's not good because there will be a lot of heat dissipation if this beta term is equal to 0. But then once you make this beta non-adiabatic term non-zero, then it moves immediately as soon as you apply small current. The trouble with this micromagnetics is that somebody must derive all these terms for you from some other theory. So somebody has to do some real theory, quantum mechanically, and then kind of export some effective expressions for different torques. And then if you have any kind of spin orbit coupling or topologically non-trivial textures, then you have to pile up more and more of these terms, and you have to study what terms are important to retain and which terms can be discarded, use some symmetry arguments, and so on. Like everything is done phenomenologically, but once some physicist tells you which term to consider, then you can just sit down, and this becomes actually a business of applied mathematics, and code this in as efficient way as possible. You can GPU accelerate these calculations and so on. So this talk actually does have this component. We are also going to solve Landau-Lisch's Gilbert equation for each of individual sticks describing classical localized magnetic moments, but we are going to consider explicitly electrons in the game. And this makes the whole calculation quite different, and one can then ask, what do we capture that these people who do this purely micromagnetics have missed? So in order to include electrons, we have to use quantum mechanics, but this is not going to be your textbook quantum mechanics. Let me remind you, in basic quantum mechanics, when we want to connect the formalism and what we teach students to what we measure, we tell students, you take an operator, you take a quantum state, you find the sandwich, which is expectation value, and then that will tell you what you're going to measure experimentally. If you measure some physical quantity described by operator A, such as spin, on 1 million copies of your quantum system, such as 1 million electrons comprising current, then the number you get is going to be given theoretically by this expectation value. But this is, of course, not sufficient if you're at finite temperature or if you're out of equilibrium, because in all of these cases, you do not have any more diskettes, pure states. Instead, you have to shift to a density matrix. So, for example, if you take a course in quantum statistical physics, the density matrix could be e to the minus beta h minus mu n in the grand canonical ensemble divided by the grand canonical partition function. Exactly that density matrix is actually written here using the green functions, which is a convenient way to run the calculations for different devices. But even this is not enough if you have current in the game. If you have a current in the game, you need a non-equilibrium density matrix. And there are many different ways to construct this non-equilibrium density matrix. For our purpose and for modeling spintronic devices, the best way is to actually use the intermediate quantity called non-equilibrium green function. There are two of them. One gives you this called retarded one that you might have heard in some courses. It gives you basically density of states. And the other one is called lesser, that tells you how the states are occupied. So if you're in equilibrium, retarded green function tells you the states, and the occupation, you don't need lesser green function, is given by Fermi distribution function. So Fermi distribution function immediately gives you occupation of these states because it's equilibrium and gives them Boltzmann solve this problem for you. But if you're out of equilibrium, there is no any kind of new magical distribution function you can stick into this equation and replace Fermi distribution function from textbook quantum statistical mechanics. Instead, you have to find this matrix G lesser that is going to tell you how these states are occupied once, for example, the bias voltage is applied or femtosecond laser pulses. And if you're in steady state non-equilibrium, you can use this G lesser as a function of energy. But if you're in time-dependent non-equilibrium, as is going to be the case all throughout the talk, you must use this G lesser, which depends on 2 times. And then if you equate T and T prime, then you get the time-dependent non-equilibrium density matrix. So that time-dependent non-equilibrium density matrix is now the proper replacement of elementary quantum mechanics. So instead of using what I discussed here in elementary quantum mechanics, you use psi, expectation value. That out of equilibrium must be replaced with a trace of non-equilibrium density matrix as a function of time times the operator. So the operator stayed the same as in textbook quantum mechanics, but this is the hurdle, how to efficiently construct this guy. So what we do in our formalism, we are actually solving this kind of equation. So if I was to solve only, and if the students were to solve only this part of this equation, that would be again a textbook von Neumann equation that replaces Schrödinger equation in the world of density matrices. But since we are considering open quantum systems connected to reservoirs from which electrons are coming in, then we have this extra term which is basically capturing the open nature of the whole quantum system, or in devices of non-electronics and spintronics, this is basically means there is a battery somewhere and 2 chemical potentials, and the current is flowing from one higher chemical potential to lower chemical potential. And it turns out that this openness of the quantum system introduces this ugly quantity, which is an integral, and then you have to solve this integral differential equation, which is a matrix equation. So then, at the end of the day, you are actually not going to really solve this by brute force, because that would be extremely expensive, and until, let's say, 2015, the computation complexity of solving this by any brute force was number of time steps to the 3rd power, and that means you cannot evolve beyond few femtoseconds. But since 2015, we have learned how to perform this calculation with linear scaling in the number of time steps, and this has changed things completely, because once you have that kind of computational scaling and solving this type of equations, you can actually evolve all the way to several picoseconds, even nanoseconds, and nanosecond is the typical scale of spintronics experiments, because this is the length of the pulse that spintronics experimentalists such as Gambardella or Hyun-Soo Yang would be injecting into their devices. There was a raised hand. I can answer any question if you want.
Yeah, can I ask a question? Or
yeah, please go ahead.
Hi, this is Bhaskaran.
Yeah.
Hi, Bran. So a very quick question. So this T and T prime, right? You have 2 times. I understand that. So you make T is equal to T prime. That becomes the center of mass time, right? T. But you also have the T minus T prime that Fourier transforms to energy. What happened to that?
This is excellent point, and you can work in many representations. So you can work in T and T prime. You can work in T minus T prime and T plus T prime, and then Fourier transform one of those. You could actually, if you want, take this TT prime and transport into EE prime.
Yes.
Or you could keep T and replace this T plus T prime with E. So these are 4 different representations of the same thing. So right now I'm working in representation in which I consider both T and T prime. So technically it looks like as if we are really finding G of TT prime, and then to get a density matrix we just say T equals to T prime. For some other considerations, especially doing the expansions and understanding, for example, the formalism you're using compared to this full TT prime, it is better to do what you are asking, TE. And I will mention then what is the connection between this stuff and what you're doing once you go into TE representation. So like, for example, that T minus T prime, T plus T prime, that will be Wigner representation. Once you convert one of those T plus T prime into E and you keep T minus T prime as the time.
Thank you.
Yeah. So this is all like a purely computational convenience. For example, in some of our papers, when we do Floquet, we actually do EE prime, and then Floquet theorem establishes connection. But in this particular talk, everything is done in the representation, and I'm explicitly considering T and T prime And then once the green function is calculated, then we say, let make t equal to t prime, which is going to spit out the density matrix. So as I said, for spintronics purposes, the most important case is taking Pauli matrix vector as operator A. And that's how we get SED. Once we have this current-driven non-equilibrium spin density, as you know from my crash course on spin orbit torque, you just need to take a cross product with that classical stick, mi of t, and that will give you torque. If you take trace of these P matrices, that would give you, with Pauli matrix, that would give you spin current flowing into the, let's say, left to right lead. If you take a trace of P matrix itself, that will give you charge current. So in other words, once you know this quantity from this red equation, you can get anything you like. Non-equilibrium spin density changing in time at a given position I, you can get torque, you can get charge current, you can get spin current, you can get local spin current, local charge current. And all of these quantities would be eventually plotted for you for different examples. So before I go on, let me give you actually a standard picture of torque which comes from this equation. So many people since 1990s have been learning how to calculate torque in a completely static fashion. Static means you set up some angle between left and right magnetization, and then you calculate that cross product of non-equilibrium spin density computed using that steady state green function because of steady state current. And what you see then is that, for example, if you consider this cobalt, copper, cobalt spin valve, which was the earliest system used in experiments, you see that torque oscillates as a function of position in this second cobalt layer. And the reason for that is like textbook quantum mechanics, because the spin in this case is oriented in this direction. The magnetization of the second cobalt is in this direction, and since the spin is not the eigenstate of Zeeman Hamiltonian, is going to precess. And that precession leads to this green stuff. This non-equilibrium spin density is precessing, and the torque is just oscillating. And according to this picture, what is then torque? Like you're gaining something and losing something, and when you integrate, you get zero. But the catch is that you're going to send electrons with different k vectors onto this second free cobalt layer, and each k vector is going to generate a little bit different precession. So like one k vector will have green, and another one would have black, and so on. And when you sum up contributions of different electrons impinging with different k parallel vectors in some kind of clean case when you don't have disorder, then when you sum them up, you see that the summed torque is going to decay. And so according to this is not zero anymore. Instead, if you integrate this blob, this area, up to this point here, that will be the total torque impinging onto the second cobalt layer. And this means also that the torque is interfacial phenomenon. You can actually see here from this first principles quantum transport calculations applied to torque, what is the thickness within which torque develops. And this was actually done in this review article by one of my previous postdoc, happens also to be from India, Kapil Devdaloy. And so this is a theoretical explanation. So like you have these different phases from different k vectors. When you sum them up, they cancel out and produce this decay. Actually, what is really weird compared to standard electronic transport of charge is that even evanescent wave functions, which decay naturally, you see the transmission of evanescent wave functions, they do not contribute to current, because something evanescent cannot propagate from left to right side of the circuit. And so they do not contribute to current, but they do contribute to torque. And typically it's about 10% contribution from evanescent wave functions. So they naturally decay, but they're only 10%, 90% is this effect of averaging over different k vectors. So now the catch is that experimentalists, all of this stuff happens dynamically. If you do this kind of calculations, everything looks statically, and you don't know like what happens once everything is flowing, moving, and so on. Experimentalists, and this is now a beautiful paper by Pietro Gambardella, which he might mention when he gives your next W2S seminar, they have already reached the point when they can dynamically monitor on the scale of few nanoseconds how the torque proceeds. So in this setup, he injects a current pulse. You can see that his current pulse is about 2 nanoseconds long. and he monitors by this complicated equipment, which I'm not going to detail because I'm not experimentalist, how the initially all spins up eventually switch to becoming all spins down. And this is example of magnetization switching or magnetization reversal, in this case by spin orbit torque, and you can also see there is non-collinearity inside due to all kinds of interactions he might tell you about. And as I said, many experimentalists these days, they do not apparently need us theorists. He just takes one of these micromagnetic codes and he can even model this whole, this is experimental image, this is theoretical image modeled by, let's say, this MUMAX. And it looks like that you could do everything classically. You do not consider electrons explicitly. You're just basically putting some terms into your micromagnetic codes, and that takes care of electrons phenologically, and you don't consider them at all. But in real life, if you think about this carefully, what will happen, and this was also in that movie, is that electron is hitting the magnetic moment. Magnetic moment is going to start moving, and that magnetic moment start moving is going to introduce a time-dependent term into electronic Hamiltonian. And now the key question, and that's the essence of this talk, is do you need to couple these two time-dependent Hamiltonian? So there's electronic Hamiltonian, which is time-dependent because of the motion of these classical magnetic moments, and there is a classical Hamiltonian which is time-dependent because either electrons are injected or because you have applied some external fields. And what we really do, we write these two Hamiltonians, and then we solve Landau-Lifshitz-Gilbert equation for these classical sticks. That becomes the new input for the previously discussed time-dependent non-equilibrium green function calculation. The time-dependent non-equilibrium green function calculation spits out the time-dependent non-equilibrium spin density, and that guy then goes back into LRG equation as the torque. And you do this over and over again at each time step to self-consistently introduce this influence of these two subsystems, one of which is quantum, the other one which is classical, and they're both evolving in time by their own equations. And here is the example. Once you do this, what will happen? So here I have a very simple spin valve of only 3 spins in the left ferromagnet and 3 spins in the free right ferromagnet, and I'm injecting a pulse of a current, which you can see being animated in this panel here. And I had this postdoc who had excellent skills in creating these beautiful animations, Marko Petrovic. And you see that as the pulse is activated, very quickly we flip all the magnetic moments from up to down. And in the process, they also generate some spin currents that are going into the ferromagnetic layer and then eventually go, this is the current which is causing the torque, and then this is the current going from the ferromagnetic layer into the lead. And now you can ask yourself, why bother with this full time-dependent calculation, which is of course very demanding as you have to solve that integral differential equation. Why not try, and this is something that Professor Data started and many people picked up on since 2006, why not just use the static time-independent green functions that I did actually use in that slide on this evanescent wave function and so on, and just sort of couple at each time when the time is just a parameter rather than a dynamical variable, NGF and LRG, and some people do use this as NGF LRG, and if you do that on exactly the same system, this right ferromagnet never switches. So in other words, there is something wrong with this NGF LRG, and it's very easy to understand what's going on. At least on this example, essentially the whole formalism, once you take everything into account, is considering that this electronic Hamiltonian does not commute with itself at different times. And this is what brings this huge difference. So this Hamiltonian at time t1 and t2 commutator is not equal to 0. While this formalism assumes that these Hamiltonians commute, and that's why it does not pick up the correct dynamics. Another way to understand this, and now comes this issue of representations. If you go in this representation that Professor Muralidharan mentioned, which is T and E representation, and then you expand this lesser green function into Taylor series, where the small parameter is dm over dt, which, assuming that these classical spins are slow, is going to be a small number, and then you do first order, you do a zeroth order term, then you have this delta m over delta t, C1 times some quantum mechanical expression, then you have plus C2, then you have delta m over delta t square, and then you have another term, and so on. So if you consider this kind of expansion, using this NEGF plus LLG means that you're only considering the so-called adiabatic limit, where everything is frozen in time and time is not considered as a dynamic variable. It means that you're considering essentially dm over dt to be so slow that this is basically zero. But this formalism, when LLG is coupled self-consistently to time-dependent density matrix for green function calculation, basically takes into account these higher order terms. And some people have been considering, let's try only one of these terms. We effectively take all of these terms to infinite order, and I will discuss maybe at the end of the talk why this could be important, because once you do that, you can pick up some experiments that are experimentally observable effects that are now in the focus of community. In particular, the first two terms will be probably the most important to consider in terms of comparing to experiments. So by the way, this term basically gives you damping, some form of damping, and then this other term, which is delta m over delta t squared, that gives you the so-called inertia. And so both of these have been explored experimentally. And so here is example of insight that this new formalism brings, which we call TD-NEGF-LLG. So like in the development of these racetrack memories, one important issue was that if you inject a current pulse, you want to know precisely where is the domain wall. And so, for example, here we have a current pulse. Here is the pulse comes in, pay attention, the wall moves. And then the pulse stops, there is no pulse anymore, and you would like the wall to stop, but the wall actually continues moving. And then we put the pulse with opposite polarity, and the wall goes back. So if there is no so-called inertial motion of magnetic domain wall, which means wall is moving with no current pulse, then you should see that the pulse comes back to the initial position, but it doesn't. This is the initial position, and this is the final position. And so there is some distance that the wall covers without any pulse being applied. And in micromagnetics community, they have estimated this motion to be huge. Like if you take this formula from micromagnetics community, purely classical simulation, it looks like that my wall should move by about 100 lattice spacings, but it moves only by 2. Then people did experiments, let's say this one from 2015 done in Kyoto by Teruo Ono's group, and they see much shorter inertial motion of domain wall, and they start invoking all kinds of phenomenological reasons, maybe it's pinholes or some disorder and stuff like that. But we actually do see that the wall moves inertially without any current pulse being active over a much shorter length scale, and some other people have noticed the same thing. This is a very recent paper, and in both of these cases, as they say, it is as if electrons, these moving electrons, and electrons are moving either because they are injected, or if there is no current pulse, the wall is moving and then dragging electrons together with them in this time-dependent fashion because of time-dependent electronic Hamiltonian. So these electrons provide the friction, and that friction or damping in the spintronics language is basically slowing down this domain wall, so that the distance that the wall moves without any current pulse being applied is much shorter than previously estimated using phenomenological theory. So this is the power of microscopic theory. Like you don't assume anything, you only write 2 Hamiltonians, and that's a microscopic really. You start from 2 Hamiltonians, and then you grind through equations. And there are no free parameters as long as you pick up some parameters of realistic materials. Everything comes from the formalism rather than you be guessing, what is the reason for this and that. So as I said, one way to understand what electrons are experiencing once this magnetic moment starts moving is that you can consider this problem, which is another very important problem from spintronics, which is what happens, for example, and you saw that in that movie, when this localized spin starts precessing. So when the localized spin starts precessing, it is actually going to inject a fast precessing electronic spins into neighboring normal metal. And this phenomenon is called spin pumping. So it is generation of time-dependent spin current in the absence of any bias voltage. So many years before this was discovered theoretically by Gerrit Bauer and collaborators in early 2000s, in 1990s it was popular to discuss the so-called adiabatic charge pumping, and this is the same sort of phenomenon because you have, for example, a quantum dot and you apply two different time-dependent potentials like gate voltages, and you get current being pumped, and the current could even be topologically quantized, which is part of Nobel Prize for Thales in 2016, and it all happens without any bias voltage. But this experiment had to be done at a very low temperature, and it was inconclusive because you can have all kinds of parasitic effects. On the other hand, this spin pumping looks the same because the role of these two potentials is now played by two components of magnetization rotating. But unlike this adiabatic charge pumping, which is typically a 1 Kelvin phenomenon to preserve the phase coherence, quantum coherence of the whole quantum dot setup, what happens here is that you can observe this at room temperature. And so what is the catch? Well, the catch is that it turns out this pumping is interfacial phenomenon. And since interface is always shorter because it's geometrical, so the length of this interfacial region is always shorter than this dephasing length scale over which electron loses its ability to superimpose its quantum states, you can have this spin pumping as a room temperature phenomenon because it's driven by interface. So pay attention, anything interfacial requires quantum transport even if it is at room temperature. So this is the message that you learn from this spin pumping phenomenon. And then once you have this pumping, what will happen is that this ferromagnet is losing its angular momentum. And because it is losing angular momentum, you're going to see like broadened damping lines, or you could inject pumped spin current into a spin orbit material, and then using inverse pinhole effect, you're going to see the voltage. And if you measure that voltage, you will detect that spin pumping is occurring. So the reason why I'm mentioning spin pumping is that if you remember the movie I gave you at the beginning of the talk, in that movie you saw that some of these white sticks were precessing, and naturally they're going to pump each of them individually spin currents. And now imagine how complicated that becomes. You inject electron excites this single magnetic moment to precess. That moment starts pumping current, which means now there is a new current in the game which is affecting magnetic moment again. So it's a self-consistent problem, and self-consistent problem in any kind of science must be solved on the computer, which is why you need to solve this over and over again. It's a small time step, and the time step in all of our calculations for all kinds of reasons of numerical stability has to be 0.1 femtoseconds. So essentially, even if we want to evolve for 2 nanoseconds, as Gambardella does in modeling his experiments, we still have to do this slowly, 0.1 by 0.1 femtosecond, and that's why the computational part becomes very important, because until this linear in number of time steps algorithm became available, it was not possible to reach those time scales by evolving on such a short time scale to have stability of this green function equations. So the spin pumping itself can be actually understood very easily via this example, which I developed a decade ago for my own understanding, but these days I can also use it in teaching or testing the new graduate students coming from overseas or from the US. And basically imagine the following setup, which is like extension of something you might have seen in your introductory solid state or engineering course. Imagine we take a 1D tight binding chain. And in that 1D tight binding chain, we put one single classical precessing spin, And we might also put some barrier just to make it model some kind of tunneling, possibly junction. And now you ask yourself, what would happen if this guy is precessing? Typically, precession comes because experimentally in the experiments of the kind as shown at previous slide, somebody sending microwaves. But as I said, in our experiments or simulations, the precession will come because you're injecting current pulses. So in any case, the reason is not important. Imagine the precession is steady. And it's very difficult to answer this question intuitively, because when you study quantum mechanics, they tell you this is the time-dependent Schrödinger equation, and you write it down, but then you give up very quickly on it and you switch to something that students can handle, which is time-independent one, and maybe you do some perturbation theory later in the course, but none of us actually has a very good intuition with time-dependent quantum mechanics. And this is why this question is difficult to answer. But in this case, there is a helper, which is that you could take the Hamiltonian of this time-dependent 1D problem, and the chain is infinite 1D tight binding model, as you can see from here, and you could make it time-independent by performing unity transformation to rotate the whole Hamiltonian into the frame moving together with the black vector. And once you do that, the Hamiltonian becomes time-independent, there is no any more t, and because of this term from the time-dependent Schrödinger equation, you get extra Zeeman term. And what the Zeeman term effectively does, and to solve this in the fashion of quantum transport theory, we actually split infinite tight binding chain into semi-infinite lead, left one, right one, and then we only consider these two sides explicitly. So this guy is going to split the leads into left lead, half metallic ferromagnet down, left lead, half metallic up, right lead down, right lead up. And what used to be frequency of precession would now become bias voltage. So it looks like that we have effectively mapped a time-dependent, complicated quantum transport problem into a 4-terminal time-independent problem in the rotating frame. And in this 4-terminal problem, we simply have to solve something like Landau-Buttigieg transmission functions. For example, you have to find transmission for spin to go from left to right lead because it's higher chemical potential here, lower chemical potential here. Then this spin is going to go from right down lead to left up lead. And this is exactly pure spin current because you have two opposite fluxes moving in opposite directions. There is no charge current being generated, but there is a pure spin current. And this is the essence of spin pumping explained in the 4-terminal device biased by this H omega in the rotating frame. So in the rotating frame, this becomes just a problem of static quantum transport, which you can solve, for example, using Quant. You download Quant package, and you just calculate using Quant the spin resolve transmission functions, and that would give you the spin current. There's also charge current possible, which is the difference of these two transmission functions. So this is, for example, transmission function right down, probability to go into left up, or vice versa, left down to right up. And this, by the way, can be solved in Mathematica. So if I was like to engage you actively and we were in a real classroom, I could have given you our very old Mathematica notebook. And if you run the Mathematica notebook, you will get this. The pumped spin current is going to be proportional to H omega sine squared theta, where theta is this angle of the cone. And then there are some parameters which are basically properties of this semi-infinite leads. And this formula turns out to be exactly the same one that Gerrit Bauer and his collaborators have derived, but using much more complicated formalism of derivatives of the scattering matrix, which is much less transparent. And if you now take this formula and you evaluate it, you will see, for example, that when there is no barrier, there is equal pumping of left and right spin current. They are both identical, left, right. Once you introduce the barrier, the right current will be blocked. As you can expect, it goes to 0. But then you would naively say, aha, if the right current is blocked on the left, I'm going to get twice as big current, but that's naive. That's a unit theoretical physics. If you calculate rigorously, you find out that the left current, after you block the right current by this potential barrier, is going to be 4 times bigger. And so there is interference effects, which makes it twice as big as the naive expectation. Moreover, we also pick up something that is not present in the scattering theory of spin pumping of Garrett Bauer and collaborators, which is that if you have the asymmetry, left-right asymmetry of this whole structure, which is obviously introduced once you have the barrier, then you also get charge current being pumped. But this current is non-adiabatic, it is proportional to omega square. So anything proportional to omega would be adiabatic, or essentially equivalent to linear response in charge transport. This one is omega square, and there is actually a paper that we wrote on a completely different topic, which summarizes what are the conditions to get this proportionality to omega or omega square. So you can download it from our group website and study this if you're interested in the general requirements. What is the current spin or charge that is coming out of quantum system driven by harmonic time-dependent field, depending on what kind of symmetries are broken in your system. So all of these currents are eventually going to be generated in this magnetic domain wall dynamical examples I gave you. The only difference is that in those cases, as you saw from my first movie, you're not going to have one guy precessing, but there will be many of them precessing. And they're all going to send the spin currents into each other. And you can imagine how messy is this problem and why you need computer to solve all of these mutual interactions at a given 0.1 femtosecond time step. Let me also mention this paper, which was some kind of perhaps the first one to do what is called spin-to-charge conversion, which is very popular topic experimentally these days. Experimentally, it was started by Albert Firth in 2013 or so. So in this paper, we actually used exactly this rotating frame approach to tell you that the best conversion of spin pumping into charge pumping would be if you pump into edge states of 2D topological insulator. I'm not going to discuss this. I'm just showing that you can get a lot of mileage by playing this rotating frame game, but eventually these magnetic domain wall spins are not precessing all with the same frequency or on the same axis, and all of this rotating frame would not be that useful. Nevertheless, and this is a kind of message for any student, postdoc working on this, or maybe trying to work on this, it is very important when you're developing these computational tools to have these exactly solvable models. Because once you have this exactly solvable model, and we spend, I remember vividly, students and postdocs sitting in a hot summer in humid Delaware, perhaps not as humid as India, and checking this by running these codes against this analytical formula. So you have to test your code. And what is the test of the code? Well, you take this time-dependent code and you run it until you reproduce what this formula is saying. And the formula says that the Z current should be constant in time, and the other two currents should be time-dependent. And indeed, after some transient period, we do get from 400 femtosecond onward the spin current coming from this full TD energy FLG formalism. It behaves exactly like that analytical formula. Moreover, if you plot this DC Z component as a function of cone angle, we exactly get sine squared theta. And we have also checked that every number matches to, full precision. So this is an example when you're using a very simple model that can be solved without any fancy coding and, computers and whatever, paper, pencil, to test that your code is correct. Otherwise, you might have a code, publish 10, 15 papers, referees these days do not have time to look into all these details, and then you realize that all papers are wrong because somebody at some stage created a bug in the code, and the code was just spitting wrong stuff, and now you have to write, 15 corrections and stuff like that. But this kind of approach of carefully gauging your code against well-known, exactly solvable examples is preventing that kind of unfortunate fate. So now it comes into probably the most interesting aspect of the talk, and I'm guessing.
Bransilav,
yes.
I'm sorry to interrupt. Can I request you to wrap up in a few minutes?
Yeah. So I'm actually done. This is like the last thing I wanted to show you. So this is actually now firing the code on something real. Real means experiment. So this is a very nice and beautiful experiment. You might invite him to give a talk as well. This is one of the leading spintronics groups in the US and in the world, Jeffrey Beach. So he said the following: let's take two magnetic domain walls of opposite topological charge, let's apply a magnetic field and annihilate them. So why would you do this? Well, this is the kind of problem studied by string theorists, cosmologists. There are many reasons that you would like to do this in magnetism, which you cannot do with cosmic scale objects. But in this case, there is a pragmatic reason, which is that once they annihilate, you might get a spin wave, which connects spintronics to magnonics. And that spin wave can then be used for magnonics. In this case, they hit another domain wall. But the point is that the spin waves that come from this process have very short wavelength of 10 nanometers, and that is very difficult. Like magnonics offers wave computing much better than, let's say, computing with light, because with light you have to use 300 nanometer devices. Here you can have a magnonics with 10 nanometer scale structure as long as you can generate this short wavelength exchange dominated spin waves, but that's very difficult to do, and he discovered that you can do it by this magnetic domain wall annihilation. And as usual, as I said, many experimentalists do this, he actually models the whole experiment by himself using MUMAX. No need for any of us. And from that viewpoint, you know, MUMAX and GPUs have retired all of us theorists, and they're already losing job because you just run micromagnetics, and all other papers on this topic in the literature are purely classical LRG simulation. But now we fire our TD energy LRG, and what do we get? Well, first of all, in this movie, also created by Dr. Petrovich, you can see that, and let me speed up because it takes time to reach the relevant length scale of about 10 picoseconds, that magnetic domain walls are moving because of this applied magnetic field and eventually disappearing. How do we see disappearance? Well, you see here the orange line is flat. All the arrows are now pointing along the x-axis, so there are no domain walls, but they're not static. They continue precessing, and this thing precessing is exactly spin wave. So in other words, our TD energy FLRG has reproduced exactly what Beach Group got using their micromagnetic simulations. We do confirm that annihilation of two magnetic domain walls does lead to the spin wave that you have seen at the very end of this simulation. And from that viewpoint, you know, we just reproduced what they did in one dimension. They did it with the MUMAX. Why bother? But then there is extra stuff. I just gave you the story of spin pumping. So in the process of annihilation, the two domain walls are going to pump spin current. And what is being pumped turns out to be highly unusual. If you look at the Fourier spectrum of this pump spin current, and this is now completely beyond any of these analytical formulas I discussed of standard spin pumping theory, it turns out that the Fourier spectrum is continuous. So all of the pumping I discussed, these quantum dots, these precessing magnets, and so on, would always be a single peak at the frequency of microwaves or whatever is driving the precession of that magnetization. But here, as the walls are precessing and annihilating each other, they're continuously changing the frequency of precession. And that leads to the spin current pumped over the range of 1 to 27 terahertz, basically. And if you convert that pumped spin current into charge current using spin Hall voltage that Christian Bach and other of your future speakers might also mention, this is his experiment, then you will get terahertz radiation. And people have been trying to use spintronic devices, and I don't know if you have this, speakers Hyun-Soo Yang might talk about this, he has a paper on this. People have been trying to generate terahertz radiation in this range from 1 to 30 terahertz using ferromagnet, normal metal, bilayers, the spin orbit coupling, topological insulators, femtosecond laser pulses, but here we are getting unexpectedly the same thing using annihilation domain walls. And the reason why this was never noticed by anybody is because people always model this using only large equation. And unless you have electrons moving through the system back and forth due to these non-equilibrium conditions, you're never going to see this. So this is a beautiful example of what does it mean to do theoretical physics. We developed a formalism, we explain experiment, and then we predicted something completely new. What we are saying is that you are going to see spin current being pumped in a broad, ultra broadband actually, frequency range, which has never been seen in any of these other examples of either charge or spin pumping. And since I want to wrap up, let me show you this paper and kind of just advertise. This is a paper actually by Hyun-Soo Yang. again, he might mention it. In this case, he injects a current pulse, he excites dynamics of an antiferromagnet, and that then flips the magnetization of ferromagnet permalloy. And this NIO is actually very complicated multi-insulator antiferromagnetic material, but they see that if you reach some thickness of about 25 nanometers of nickel oxide, then something is switching this permalloy. And one explanation is that you're exciting a spin wave because no electron can propagate through the nickel oxide layer, and the spin wave propagates in this gray region, and the spin wave then exerts torque because spin wave also carries spin current, and that therefore it can exert torque. Spin wave exerts torque on the magnetization of the green layer. And this is kind of illustrated here, but they do not understand the detail. There is no detail here in this paper. And in collaboration with Hyun-Soo Yang, we actually decided to model his experiment. And let me actually just show you these movies, and then I will end the talk. So here is the electron coming in as a pulse. Electron is stopped. It cannot go through antiferromagnetic layer because there are no hoppings or any kind of conduction. But that doesn't stop antiferromagnet from being excited into some dynamics. So that would be that guy, the antiferromagnetic spin wave. And once that spin wave reaches the second layer, which is this ferromagnet here, if you pay attention again, the originally ferromagnet is all up. Once it is hit by antiferromagnetic spin wave, the spin goes down. So we have reproduced completely whatever he has seen experimentally by showing how you can have this current non-conservation situation. Like there is no way to send a steady state charge current here. There is a current pulse, electron is reflected. From here, spin wave is being generated, and then the spin information is transported, and it can be transported over very long distances because of low dissipation in these anti-ferromagnets. But one interesting question here is that do you need to actually allow spin wave to go through into the ferromagnet directly, or you can just prevent it by putting, let's say, as they did experimentally, copper layer, and in that case, this last layer is going to pump spin current and also excess spin torques. In other words, there are two reasons why this guy feels torque. One reason is direct injection of magnon or spin wave. The other reason is pumping of spin, electronic spin current by the last magnetic moment of antiferromagnet hit by the spin wave. And if we cut that connection between the antiferromagnet and ferromagnet, and we run the movie again, see the antiferromagnet does exhibit spin wave, but the ferromagnet doesn't move. And so this means that magnonic spin torque, and this is the perfect visual explanation of what new kid on the block, magnonic spin torque, is about, which is why this paper got a lot of attention at the end of 2019. Magnonic spin torque, which is magnon directly going into the second ferromagnetic layer and exerting this new type of magnonic spin torque, which could be done even in the absence of any electrons moving, is the reason why you eventually are able to flip the magnetization of the second ferromagnetic layer. So I'm going to skip these formal discussions, just pointing to these references. They actually describe what do we really do, how we end up with this complicated time-retarded Landau-Lifshitz-Gilbert equation, which is what is behind our formalism and explains its inner working. And we also discussed in some recent papers, again, just advertising to take a look at the references, that we were able to extract something that was missed in spintronics called geometric spin torque. So this is a summary of my talk. We developed this self-consistent coupling of time-dependent quantum transport and Landau-Lifshitz-Gilbert equation. Pay attention that Landau-Lifshitz-Gilbert equation is used in two different types of codes. One type of code is classical micromagnetics. The other type of code is atomistic spin dynamics. In both cases, you're doing exactly the same mathematics, but in classical micromagnetics, you're considering cubes of, let's say, 5 times 5 times 5 nanometers, and each cube is represented by one classical vector. In atomistic spin dynamics, you consider this classical vector sitting on each lattice site. And actually, in the case of antiferromagnets, you must use atomistic spin dynamics, which is why, also because of coupling to our quantum transport, we actually consider this to be atomistic spin dynamics rather than classical micromagnetics, but it is the coupling of a set of Landau-Lifshitz-Gilbert equation together with this time-dependent quantum transport. And once we have this machinery working, we can then capture many phenomena that were previously discussed either phenomenologically. For example, if you don't have this formalism, you would have to, one way to do it would be you calculate from classical, and people do this, there are many groups which have been doing this before us, they calculate this mi of t from some mu max or oomph or any other favorite micromagnetics codes, and then they take these trajectories they obtain from the purely classical calculation, and they stick them into some formula. And now you have to believe that the formula is correct, and that's the only thing you have. And in some of these last few slides, which are kind of boring theoretical stuff, I did not go into details. We actually show explicitly that some of these formulas are just low-order approximations to our full formalism. So if you do this approach of using purely classical micromagnetics and sticking in, you're going to miss things which are embedded into the self-consistent nature of this full microscopic problems. But in our case, we don't have to think about anything. Every possible torque and every possible pumping and every possible self-consistent mutual interaction between quantum and classical system is automatically taken into account once you start from one Hamiltonian, which is quantum of electrons, and the other one, which is classical for local spins. Okay, so this is the end of my talk, and I apologize for maybe taking a little bit more time.
Okay, thank you so much, Bransilav.
Yes.
Excellent lecture cum tutorial. It's really nice to see a variety of topics which are of course interconnected. I have to go in about 7 minutes for my next meeting. So unfortunately there is not much time, but I see one quick question from Sriram. So he's asking, can you please comment on anti-damping on spin bumping? What is the reason for low effective damping compared to single ferromagnetic damping value?
Yeah, so this is actually an excellent question which I skipped because of not having time. So if you go, and this is probably one of the best papers that we did with Utkarsh Bajpai, my student who was so inspired by NISR, trying to understand better, you know, we develop this formalism computationally, but then you have to understand what is the formalism doing. So if you write analytically what this introduction of non-equilibrium density matrix does to the LLG equation, you end up with this guy. So this is an LLG equation which has a standard M cross B term, but then all the dampings, pumpings, and all of this stuff is now embedded into this kernel, which is time retarded. It depends on all previous times. And this is essentially an attempt that many people tried before us but failed to do the so-called integrate electrons out. Ideal thing for the experimental community would be all of these effects I'm talking about, you somehow remove electrons by some analytical manipulations, and then you provide equation. And actually Christian Bach has papers when they pick up one of these integrate out formulas and adds into the code and then tries to model his experiments. But these approximations are not possible always. Like they require all kinds of limits. So in one limit, you could expand this kernel into Taylor series, and then you will recover something which does look like ordinary Landau-Lifshitz-Gilbert equation. However, unlike ordinary Landau-Lifshitz-Gilbert equation, it has actually time-dependent constant. So like in standard Landau-Lifshitz-Gilbert equation, this constant multiplying m cross dm over dt would be just a number. Here it's not a number, it depends on time. And then the second order term is this thing I called inertia. And essentially what this thing are doing, in addition to this standard Gilbert damping, they also introduce something called non-local damping. So for example, non-local damping, here is an attempt to capture that non-local damping. So this pumping that goes into the leads effectively acts like asterisk damping. So everything looks like as if you have a Landau-Lifshitz-Gilbert equation with standard m cross dm over dt damping plus another damping. and that another damping is picked up by our TD energy FLG formalism. And actually, in one of these complicated plots that you would have to, I would have to go and read my own paper to remember all of these details. But in one of these complicated plots, we actually give you the ratio between additional damping that is generated by this whole formalism capturing these electrons pushed out of equilibrium by the dynamics of mi of t, and standard Gilbert damping that you would put by hand. And the ratio is about 2. So the new damping coming from non-equilibrium electrons driven out of equilibrium by the dynamics of m of t, which you do not have in any micromagnetic codes, is twice as large as the standard damping you put into the game. And now you can ask me, how is this important? Do we see this experimentally? I found out a few months ago that Christian Bach has a paper when he has noticed Gilbert damping measured by 2 different procedures in the lab having exactly that ratio. And that is telling you essentially that we are very close to something real. So he has exactly that. We get 2.4 ratio. In this figure, he gets 2.3. The ratio between Gilbert dampings generated by these dynamics of magnetic moments jerking electrons around and the standard Gilbert damping that you have in every micromagnetic code. So this is essentially, in a nutshell, what this formalism is doing. Aside from telling you that there is pumping out of the system, torques and stuff like that, it is unraveling additional source of damping due to these non-equilibrium electrons, which is present even in the absence of spin-orbit coupling. Like a conventional Gilbert damping with this constant lambda must require non-zero spin-orbit coupling. But this damping that we see due to electrons being driven out of equilibrium by the dynamics of mi of t would be there even if spin-orbit coupling is 0.
Okay, so I can just add that experimentally recently we have also seen this anti-damping in LSMO magnonics. The paper just published last week in Nanoscale. So LSMO platinum, there is something called this anti-damping related to the spin diffusion length. So unfortunately, I do not have time to go into details. I suggest to...
Oh, okay. By the way, here is the paper of Christian Bach. I actually have it.
Yeah.
This is his paper, which says that you have some discrepancy in measuring Gilbert damping by 2 different experiments, which is suggesting this non-local damping due to pumping out of non-collinear textures.
Yes. Okay, quickly, I have only 2 minutes. Mr. Akshat Misra, so he's asking, how well have these theories taking spins classically performed when compared with experiments? So very brief answer, please, Bransilav.
Can you repeat the question?
So he's asking, how well have these theories taking spins classically performed when compared with experiments?
Oh, okay. So, like, you can ask Gambardella this question because he is, and all other experimentalists. As I said, most experimentalists run these purely classical simulations by themselves. They never, even have any theorists in the group. So here is example of Gambardella's experiment where you see, measurement, and then you see everything reproduced by purely LLG micromagnetics calculations. So in regards to what I was discussing, and from this viewpoint, you could say you don't need all of the stuff I'm talking about. But if you look at my stuff, for example, and this is one of the best, topics for you to, as a take-home, to take away. In this experiment, they also did their own theory. There is no theorist on this paper. They just take the code and run by themselves. And they reproduced everything phenomenologically, that there will be an annihilation and there will be a spin wave. But what I'm saying, we reproduce the same thing, but we predict new stuff. Like you can never get this from micromagnetics codes or any other theory with simple formulas and stuff like that. This must be done numerically. We check this in many different ways. This result only comes from this algorithmic numerics. ultra broadband pumping. And moreover, the spectrum of spin waves that you would get from purely classical calculations that this beach has turns out to be different than the spectrum we get. So like classical, as I mentioned, using classical spins dynamics to model localized magnetic moments is really justified formally only when S goes to infinity, H bar goes to 0, and there is no entanglement between quantum states of localized spins. And if you want to do anything better than that, you would need to go to that new stuff, quantum spin torque, which is my completely different talk. So from the viewpoint of present spintronics, it looks like as if when you are at room temperature, even if your spin is not infinite and your H bar is never 0, things look quite good for the micromagnetics. But you need to add these corrections due to moving non-equilibrium electrons. As you go to low temperatures, or you start playing with, let's say, quantum antiferromagnets or quantum spin liquids, then of course all of the classical description is going to be broken. And this is really the real issue is why do people use LLG and micromagnetics to model antiferromagnets? Because, for example, as I told you, this nickel oxide is a MOT insulator combined with charge transfer insulator. And all other physics communities will be modeling this material using TJ model, Hubbard model, and stuff like that. But in spintronics, we just say this is a bunch of up and down sticks, as is my movie. So this is the real question, like, this description of using LLG and classical sticks has to be broken for more complicated materials, even at room temperature. But for regular ferromagnets, it looks like even if the spin is not infinite, spin is 5/2 or 3/2, LLG works quite good as long as you're at high enough temperature.
Okay, thank you. Ashwin Tulapurkar has a question. I read it. The spin torque oscillations were till 10 or more atomic layers in the simulation. Isn't the spin current absorbed within one atomic layer? Is the spin pumping voltage calculated by you, AC voltage?
Which experiment are we talking about?
I don't know. So Ashwin, if you can come in, that would be good.
So normally the spin current is absorbed by almost within one layer of atom, right? In the ferromagnet. But in the
yeah. Spin current is all. Yeah, that's actually that's an excellent question, and I have a non-verbal explanation for that, which is my picture. So you could say that topic you are asking about is here. So like
no, it
in
was
this figure.
It was before this. You summed over all the k vectors and found spin torque is oscillating within the ferromagnet. Yeah, I think this one. Yeah.
Mm-hmm. Okay, but in this specific case, you could calculate torque in the following fashion. So you could calculate what is the spin current at this plane. Then you would calculate spin current at this plane, which is 0. And the difference of spin current at this plane, IS1 and IS2 would be torque.
But if my lead is not so thick, if the lead is only few mono layers of ferromagnet, still we get spin torque.
Oh, you would get a spin torque, but this simply means that there would be some non-zero current coming out. But the torque would still be the difference of the current at this plane and this plane.
And I don't know if there's any experiment which has shown that the spin torque will oscillate as a function of ferromagnetic thickness. But according to this calculation, it should oscillate.
Yeah, it should oscillate if you make the layers very thin, but one has to also be aware that this calculation is kind of for illustrative purposes. Real devices are never super clean. This one is super clean. So once you take disorder and stuff like that, these oscillations would be averaged over the many realizations of disorder. So like all of this K vector business and stuff like that is because I'm considering perfectly clean translation invariant device, but the real system is never going to be perfectly clean.
Yeah, thank you. And I have one more question.
Ashwin, can I request that you kindly write that question to Bransilav by email?
Yeah, sure.
I'm really getting
like one, I'm willing to continue answering question. If you want, you can stop recording and then, just, if you want me to.
So what I'm doing, Branislav, I'm making you the host now after this, and you can continue discussion and close when you are ready. Okay.
Yeah,
so
exactly.
Before I leave, I like to again clap on behalf of our team. And I'm really grateful to Bransilav for this excellent lecture, like a tutorial. It's so late in the night, now it's early morning for him. And I'm also sincerely thankful to Bhaskaran, who has suggested your name. It was really excellent choice. And thank you so much for your
Thank you, Brian. Thank you, everyone. Thank you. Hopefully
you will invite us one day, both me.
Of course. Let's Corona go, and of course, I'm looking forward to that. Thank you. Bye-bye.
Thank you. Yes. So if there are any other questions,
I have one more question which I have actually typed in the chat box. So my question is, the spin pumping voltage that you calculated, is it AC voltage or DC voltage?
Let me answer this. Let me actually mention also, like, this calculation is our own because I wanted to check by yourself, but this is my favorite paper on this topic of averaging, summing up what is decaying. So if you want to get more details about this specific cobalt, copper, cobalt, take a look at this phys review of K Shia from 2008. So you ask for the voltage.
Yeah, the spin pumping voltage.
Yeah, so the spin pumping voltage would be DC because of the fact that there are 3 spin currents and 3 components. But you see what happens, this fast precessing spin are basically washed out on some length scale L omega, which is square root of d over omega. And so what happens at the end is just a DC component. So essentially, the other thing is that if you look at the spin hole, if there are 3 spin currents and you position your voltmeter here, you're basically detecting inner spin hole effect due to SZ, and that one is DC. So the one which is measured at the end is DC. Of course, experimentally, I don't know what they really measure. Probably there is some AC measurement. But
no, you can also measure the AC spin pumping.
You can, yeah. And if you convert other 2 components, so traditionally people have been converting only SZ. But in this paper, again by Christian Bach, they do say spin hole voltages from AC and DC spin currents. So this is because you can have DC spin current, like if only a magnetization is precessing, the Z along the Z axis, the Z current is DC, the other 2 are AC. So most of the people since 2006, starting with Eiji Saito, have been converting that Z component into, which is DC current, into DC voltage. But in this paper, you can find AC spin current, which is X and Y, being converted into AC spin hole voltage. And I would actually like to do that because here I have a time-dependent current, the Z component, and if I convert that one into charge, that charge would generate terahertz in the continuous range from 0.5 to 27 terahertz.
Okay. Thank you very much.
Okay, thank you, Branislav, for all the time. I think it's too late for you now.
Yeah.
All right, thanks a lot. We'll correspond for further questions.
Yes, if you have any questions, you want to do anything by yourself and you need help, please let us know.
Sounds good. Yeah, absolutely. Okay. Thank you.
No problem.
Thanks.